All right, this is CS50, and this is the start of week 4. And as you may have heard or read, the world has been ending. Going all around the internet has been knowledge and awareness of a bug in a programming language called Bash. And this has been wonderfully branded as shell shock, or the bash door, but articles like these have not been uncommon. And in fact, many of them bring back memories of Heartbleed, which you may have noticed in the press back this past spring, which was similarly fairly dramatic. Now, of those of you here today, how many of you have, even if you don't understand what it's all about, heard of shell shock? All right, and how many of you have computers that are vulnerable? Okay, there should be far, far more hands up right now for reasons we shall see. Let's take a look at what's been going on in the media and then explain it a bit here for us technically.
Security experts have warned that a serious flaw could be about to affect hundreds of millions of the world's web users. But what exactly is the bug that's been dubbed shell shock, and what does it do? Well, shell shock is also known as the bash bug for the software it exploits. Hackers use a virus to scan vulnerable systems, running Linux and Unix operating systems, and then infect them. Bash is a command line shell. This lets users issue commands to launch programs and features within software by typing in text. It's typically used by programmers and shouldn't be open to the wider world, though shell shock changes that. Well, worryingly, some analysts warn it could be a bigger threat because shell shock allows complete control of an infected machine, whereas Heartbleed only allowed hackers to spy on computers. It's so serious, it's been rated a 10 out of 10 for severity by the National Vulnerability Database. 2/3 of all web servers are at risk, including some Mac computers. Well, make sure you patch your systems now. Anyone hosting a website running their affected operating systems should take action as soon as possible. Anyone who can afford it should look to their monitoring and web application firewalls to look out for any attacks.
Worst thing that could happen is that somebody would write code that would automatically go and scan the internet and would infect all of these computers. And once they do that, well, the worst thing they could do is just delete everything or shut sites down. So we could see damage from that point of view, where we would have malicious people who would just decide to cause havoc by bringing systems down or deleting files and things like that.
Some say this is one of the most difficult to measure bugs in years, and it may take weeks or even months to determine its ultimate impact.
So all of that is true, but the funny thing is almost all of the imagery you just saw, except for maybe the keyboard, has nothing to do with the bug whatsoever. Servers and wires and so forth, it's sort of tangentially related, but at the core, it's actually pretty familiar what's going on here. In fact, let me go into our CS50 appliance. Let me go ahead and maximize the terminal window here. And you guys have been using this, or the embedded version thereof, in gedit in order to write programs, type commands, and so forth. And this is actually, and has been for weeks, Bash, B-A-S-H. This is the Born Again shell, which is just a fancy way of saying this is a program that has a blinking prompt, effectively, that sits there waiting for input for you. And it's the command line interface via which you guys have been running commands and ultimately compiling and then running programs. But Bash is also a programming language in the following sense. You know that there are commands like cd and ls and also clang and others, but you can define your own commands by implementing them in Bash. Now, we're not going to go into great detail as to Bash, the programming language, but know, for instance, that at the moment, there's no command called hello. So it can be found in one of these packages. It's not installed on my computer. Ask your administrator. But if I want there to be a program called hello in Bash or at my prompt, I can actually use syntax that's quite like C. It's not quite the same, but it looks pretty similar to a function, albeit missing some details. Nothing seems to happen. But now if I type hello, you can actually write a program not in C, not in Java, not in another programming language, but in Bash itself. Now, the key here is that I wrote the name I wanted to give this new command, and the parentheses are also symbolic of this being a function. As an aside, you can also do fun things, and in fact, even on Mac OS, this is a program called Terminal that comes built into anyone's computer that has a Mac in this room, and you can do similar things in Mac OS. But you can go more beyond that. And this is a little tangential, but it's kind of fun. I was reminded this morning when thinking this through of a little game I used to play with one of CS50's former TFs, whereby anytime he would walk away from his keyboard with his screen unlocked, I would execute a command like this. Say, hello. And now anytime he came back to his keyboard after I cleared the screen and he would sit down, try to do some work, list the contents of his directory.
Hello. Hello.
So in fairness, it wasn't actually hello. It was usually something more akin to that
Beep.
I would. So his computer would swear at him anytime he actually sat down at his keyboard. And very quickly, he figured out not to leave his screen unlocked. But this just suggests the sort of stupid fun that you can have with something like Bash. But it's a little more serious, to be sure, than that. And in fact, this is one of the most dangerous and long-lasting bugs that has really hit the world globally. This bug has been around for some 20 years, and you'll be struck in just a moment by its relative simplicity. So this is a representative command that if you own a Mac, literally right now and you have your lid open, you can try typing into that program called Terminal. Terminal is under Applications, Utilities. For once, Windows users don't have to worry about this particular threat. But those of you with Macs can type this into a window like I'll do here. And if you do type that into this program called Terminal, like I'll do now, if you see the word vulnerable, your computer is vulnerable to exploitation. Now, what does that actually mean? And this is admittedly some pretty crazy syntax, but let's at least draw out some of the interesting aspects. So there's some syntax that looks a little familiar, at least from C and programming more generally. I see some parentheses, semicolons, curly braces, and such. But it turns out that this stupid thing here in yellow is essentially a function that does nothing. The colon means do nothing, and the semicolon means stop doing nothing. So inside of these curly braces, the fact that I have an equal sign to the left, this is essentially creating a command or a variable called x and assigning it that yellow bit of code there. That could be something like echo hello or say beep or something akin to that. But notice if your eyes wander further to the right, there's more to this line than just the end of that semicolon, echo vulnerable, and then beyond that there's even more, another semicolon bash dash c colon. So long story short, this line of code is sufficient for compelling a computer that's vulnerable to doing something that you want it to do, because there's a bug in Bash whereby even though Bash was supposed to stop reading lines of commands right there after the yellow text, for a 20-plus-year-old bug, Bash has actually been reading beyond that semicolon and pretty much doing what it is told. So what's the implication of that ultimately? I just said echo hello or echo vulnerable, but what if you did something actually malicious, like rm-rf star, which you might not have ever typed before, and frankly, you probably shouldn't too soon because you can do a lot of damage with it. Why? Rm does what, of course? Removes. Star means what? All, so it's a so-called wildcard, so it means delete everything in the current directory. -r happens to mean recursive, which means if what you're deleting is a directory and inside of there is other files and other directories, recursively dive into there and delete all of that. And -f is the worst of them all. Anyone know what -f means here? Force. So force means even if this is a bad idea, do it without prompting me for further confirmation. So, we laugh at this, but frankly, I probably type this multiple times a day, because the reality is it's the fastest way to delete a whole bunch of stuff, but even I have done some damage. But if you were to trick a computer into defining some stupid variable or function called x, but then tricking the computer into executing beyond the boundaries of that function, beyond that semicolon, you could indeed trick a computer into executing something like rm-rf, or the email command, or the copy command, anything literally you can do with a computer, whether it's deleting files, creating files, spamming someone, attacking some server remotely. If you can express it with a command, you can trick a computer into doing that. Now, what's an example of how you might do this? Well, there's a lot of computers on the internet running Bash. All of us Mac users are among them. A lot of Linux servers are among them as well. And Unix servers. Windows, again, gets relatively off the hook unless you've installed special software. Now, a lot of servers, for instance, run web servers. And in fact, Linux is perhaps the most popular operating system to run on computers on the internet that are serving up web pages. Now, as we'll see later in the semester, when you send a request from your browser, Chrome, Internet Explorer, whatever, to a remote server, it turns out that even though you just type www.example.com, your browser is sending a message that's a little more arcane, like this. But notice a little something strange. The first two lines I've never seen before, but they don't look particularly threatening. But notice what I've stolen for the third line here. If a bad guy were to send a message like this from his or her computer to a vulnerable Mac or a vulnerable Linux server, the funny thing is that bash, that simple little command prompt, is omnipresent and is often used to essentially execute the contents of a message that it receives. And by that logic, you can trick a web server, therefore, by sending something like user agent, which usually is supposed to say the name of your browser, user agent Chrome, user agent Internet Explorer, user agent Firefox. This is just your browser's way of identifying itself. But if a bad guy very cleverly says, I'm not going to tell you what my browser is, I'm instead going to send you this cryptic-looking thing with an rm-rf star in it, you can literally trick a vulnerable web server on the internet into executing exactly that and therefore deleting all of the files. And frankly, that's not even the worst of it. You can do anything. You could start a distributed denial of service attack if you sent this message to whole bunches of web servers and then had them all descend, for instance, on harvard.edu servers. And you can sort of bang the heck out of them via network traffic that was otherwise triggered by this bad guy. So long story short, almost everyone in this room who owns a Mac is vulnerable to this. The silver lining is that unless you're running a web server on your laptop, and unless you're actually configured it to allow something like SSH into it, you're actually safe. It's vulnerable, but there's no one trying to get into your laptop. So you can sort of rest assured. However, Apple will soon be updating a fix for this. The world of Linux has already released a number of fixes for Fedora and Ubuntu and other versions of Linux, and indeed, if you run update 50 in the appliance, even that too will be updated and corrected, but that too has not really been vulnerable, because unless you've tinkered with the appliance and made your laptop publicly accessible on the internet, which it's not by default, you've actually been fine because of firewalling and other techniques. But it's an extreme example of a bug that we've lived for literally 20 years, and who knows if someone all this time has known about it. And in fact, this is one of the fundamental challenges that we'll see later in the semester about security, is that just like in the real world, the good guys are at the disadvantage. To keep the bad guys out, we have to make sure that every door is locked, that every window is secure, that every point of entry into a home is secure to keep the bad guys out. But what does the bad guy have to do to actually compromise your home and steal from you? He or she just has to find one unlocked door, one broken window, or something along those lines. And it's the same thing in computer security. We can write millions of lines of programming code and spend hundreds or thousands of hours trying to get it correct. But if you make just one mistake in correctness, you can put the entire system, and indeed in this case, the entire internet and world, at risk. So if you'd like to learn more about this, go to this URL here. There's no need for action tonight unless you're among those more comfortable that have been running your own web server, in which case you should, in fact, update your software. And this, too, is a title of a speech and now a paper that we've linked on the course's website for today. It was by a fellow named Ken Thompson, who was accepting a very famous award in computer science, and he gave this speech some years ago essentially on this same topic, and asking folks the question, should you really trust, ultimately, the software you've been given? For instance, we all have been writing programs, and we've been compiling them with Clang. And to your knowledge, have you written any programs for CS50 where there's a back door of sorts, there's a way that a bad guy, if running your program, could take over your computer? Probably not, right? Mario and Greedy and Credit, these are all pretty small programs. You'd have to be pretty bad if you actually made your whole computer vulnerable after writing 10 or 20 lines of code, or at least unaware of some of the security implications. Now, I say that facetiously, but we're going to see today and this week, it's actually really, really easy to be bad and make even short programs vulnerable. But for now, at least, realize that the question being asked here is about Clang and a compiler. Why have we been trusting Clang for the past 2 or 3 weeks? Who's to say that whoever wrote Clang didn't have an if condition in there that essentially injected some zeros and ones into every program it compiles that would let him or her access your computer when you're asleep and your laptop lid is open and your computer is running? Right? We have this sort of honor system right now where we trust that Clang is legit. You trust that the appliance is legit. You trust that literally every program on your Mac or PC is trustworthy. And as this simple bug suggests, even if it's not malicious, that's absolutely not likely to be the case. So you should be scared as hell. Frankly, there's no simple solution to this other than a sort of societal awareness of the increasing complexity that we're building on top of our computer systems and how increasingly vulnerable we might very well be. Now, with that said, Breakout. So Breakout is problem set 3, and Breakout is a game from yesteryear that you might recall, but for us in problem set 3, it allows us to take things back up a notch so that when we are writing programs, even in a terminal window like this, we can actually run, ultimately, graphical programs not unlike those we had access to in Scratch. So this is the staff's implementation of Breakout, which is just this brick-breaking game that you move your paddle back and forth, and you hit the ball against those colored bricks up top. So this is bringing us sort of back to where we were able to be very quickly with Scratch, and now with C implementing our own graphical user interfaces. But more than that, this problem set represents the first in which we're giving you a bunch of code. And in fact, I bring explicit attention to this because especially for those less comfortable, this problem set, at least at first glance, is going to feel like we've taken it up a notch. Because we've given you, for some of the search and sorting problems in the P set, a bunch of code that we wrote, and a couple of comments that say to do, where you have to fill in the blanks. So not too scary, but it's the first time we're handing you code that you need to first read, understand, and then add to and complete it. And then with Breakout, we're going to do the same, giving you a few dozen more lines of code that frankly give you a lot of the framework for the game, but stop short of implementing the bricks and the ball and the paddle. But we do implement some other features. And even that at first glance, again, especially if less comfortable, might seem particularly daunting, and you think there's so many new functions you need to wrap your mind around. And that's true, but keep in mind, it's quite like Scratch. Odds are you didn't use all of the puzzle pieces in Scratch. Odds are you didn't care to wrap your mind around all of them, because all it took was a quick glance to understand, oh, that's what I can do with that puzzle piece. And indeed, in problem set 3's spec, we'll point you at the documentation that will introduce you to some new functions, and ultimately the programming constructs you use, conditions, loops, variables, and functions will be identical to what we've seen thus far. So indeed, what we'll give you is some sample code that lets you create a window that looks not unlike this, and ultimately turn it into something quite like this. So take advantage of CS50 Discuss, Office Hours, and more, and take comfort in the fact that the amount of code you have to write is actually not all that much. The first challenge is just to acclimate yourself to some code that we've written. Any questions on PSET 3, shell shock, or otherwise?
It seemed like going through with Breakout that code was almost an object-oriented style, but I thought C was an object-oriented programming.
An excellent question. So in looking through the distribution code, the code we wrote for PSET 3, for those familiar, it looks like it's a little object-oriented. Short answer is it is. It's an approximation of how you might do object-oriented code using a language like C. But it is still ultimately procedural. There are no methods inside of the variables, as you'll see, but it is reminiscent of that. And we'll see that feature again when we get to PHP and JavaScript toward the end of the semester. But for now, think of it as a hint of what's to come. Good question. All right, so merge sort was how we left things last time, and merge sort was cool in the sense that it was so much faster, at least based on the cursory tests we did last week, than, say, bubble sort, selection sort, insertion sort. And what was neat, too, is just how succinctly and cleanly you can express it. And what did we say was an upper bound on the running time of merge sort? Yeah. N log n, right? N log n. And we'll come back to what that really means or where that comes from, but this was better than what running time that we saw for bubble selection and insertion sort? So n squared. N squared is bigger than this, and even if it's not quite obvious, know that log n is smaller than n. So if you do n times something smaller than n, it's going to be less than n squared. It's a bit of intuition there. But we paid a price for this. It was faster, but a theme that started to emerge last week was this trade-off. I got better performance time-wise, but what did I have to spend, on the other hand, in order to achieve that? Say again? Memory, or space, more generally. And it wasn't super obvious with our humans, but recall that our volunteers were stepping forward and stepping back as though there's an array here, and as though there's a second array here that they could use, because we needed some place to merge those folks. We couldn't just swap them in place. So merge sort leverages more space, which we didn't need with the other algorithms, but the upside is that it's much faster. And frankly, in the real world, space these days, RAM, hard disk space, is relatively cheap, and so that's not necessarily a bad thing. So let's take a quick look, a little more methodically, at what we did and why we said it was n log n. So here are the 8 numbers and the 8 volunteers we had last time. And the first thing that merge sort told us to do was what? Say again? Divide in 2, right? This is very reminiscent of the phone book, of divide and conquer more generally. So we looked at the left half. And then once we said sort the left half of the elements, what did we next say? Sort the left half of the left half, which allowed us to, after dividing it in two, focus on 4 and 2. How do you sort a list now in yellow of size 2 using merge sort? Well, divide it in half and sort the left half. And this was where things got a little stupid briefly. How do you sort a list that's of size 1, like this number 4 here? It's sorted. You're done. But then how do you sort a list of size 1 when it's the number 2? Well, same thing, but now what was the third and the key step in merge sort? You had to merge the left half and the right half. And once we did that, we looked at 4, we looked at 2, we decided, all right, obviously 2 comes first, so we put 2 in its place, followed by 4. And now you have to kind of rewind, and this is sort of characteristic of an algorithm like merge sort. Rewind in memory. What was the next line of the story? What should I be focusing on next? The right half of the left half, which is 6 and 8. So let me just step through this without belaboring the point too much. 6 and 8, then 6 is sorted, 8 is sorted, merge them together like that. And now the next big step is, of course, sort the right half from the very first step of this algorithm. So we focus on 1, 3, 7, 5. We then focus on the left half of that, the right half of that, and then merge in 1 and 3, then the right half, then the left half of it, then the right half of it, merge it in, and now what step remains? Merge the big left half and the big right half, so 1 goes down there, then 2, then 3, then 4, then 5, then 6, then 7, then 8. So now why is this ultimately revealing, especially if n and logarithms more generally rather escape you, at least in recent memory? Well, notice the height of this thing. We had 8 elements, and we divided it by 2, by 2, by 2. So log n, log base 2 of 8 gives us 3. And trust me on that, if a little hazy on that. But log base 2 of 8 is 3. So we've done 3 layers of merging. And when we merged elements, how many elements did we look at on each of those rows? A total of n, right? Because to merge the top row, even though we did it piecemeal, we ultimately touched every number once. And in the second row, to merge those lists of size 2, we had to touch each element once. And then really clearly in the last row, we had to touch each of those elements once, but only once. So herein lies then our n log n. And now just to make things a little more formal for just a moment, if you were to now analyze this at a sort of higher level and try to decide, well, how might you go about expressing the running time of this algorithm just by looking at it and not by using a contrived example? Well, how much time would you say a step like this in yellow would take? If n is less than 2, return. That's big O of what? So I'm seeing 1, so 1 step, maybe 2 steps because it's if and then return, but it's constant time, right? So we said big O of 1, and that's how I'll express this. T, just be running time. N is the size of the input. So T of n, just a fancy way of saying the running time given an input of size n, is going to be on the order of constant time in big O of 1. But otherwise, what about this? How would you express the running time of this yellow line? T of what? You can kind of cheat here and answer my question cyclically. So if the running time in general, we just say is T of n, and now you're kind of punting here and saying, well, just sort the left half and then sort the right half, how might we symbolically represent the running time of this yellow line? T of what? What's the size of the input? N over 2. Why don't I just say that? And then this is another T over N over 2. And then again, if I merge 2 sorted halves, how many elements am I going to have to touch total? N. So I can express this, just to be kind of fancy, as the running time in general. T of n is just the running time of T over N over 2, plus T of N over 2, left half and right half, plus big O of n, which is probably n steps, but maybe if I'm using 2 fingers, it's twice as many steps, but it's linear. It's some number of steps that's a factor of n, so we might express this as this. And this is where now we'll punt to the back of our high school math textbook, where that recurrence ultimately ends up equaling this, n times log n, if you actually do out the math more formally. So that's just 2 perspectives, one numerically with a hard-coded representative example using 8 numbers, and a more general look at how we got there. But what's really interesting here is, again, this notion of cycling. I'm not using for loops. I'm kind of defining something in terms of itself, not only with this mathematical function, but also in terms of this pseudocode. This pseudocode is recursive in that 2 of its lines is essentially telling it to go use itself to solve a smaller problem of smaller size, and then again and again and again until we whittle it down to this so-called base case. So let's actually draw a more compelling takeaway from this as follows. Let me go into gedit and take a look at some of today's source code, in particular this example here, sigma 0, which apparently adds the numbers 1 through n. So let's see what's familiar and unfamiliar here. First, we have a couple of includes, so nothing new there. Prototype. I'm a little hazy on this after a few days, but what did we say a prototype of a function is? What's that? We announce it. So you are teaching Clang, hey, not actually implementing this yet, but somewhere in this file, presumably, is going to be a function called what? Sigma, and this is just a promise that it's going to look like this. It's going to take an integer as input, and I can be more explicit and say int n, and it's going to return an int, but semicolon means, I'll get around to implementing this a little later. Again, Clang is dumb. It's only going to know what you tell it top to bottom, so we need to at least give it a hint of what's to come. Now let's look at main here. Let's scroll down here and see what main is doing. It's not that long of a function, and in fact, the construct here is familiar. I declare a variable n, and then I pester the user again and again for a positive integer using getInt, and only exit out of this loop once the user has complied. Do while we've used to pester the user in that way. Now this is interesting. I declare an int called answer. I assign it the return value of a function called sigma. I don't know what that does yet, but I remember declaring it a moment ago, and then I'm passing in the value that the user typed in, n, and then I report the answer. Well, let's scroll back for just a moment. Let's go ahead into this directory, make sigma 0, and actually run this program and see what happens. So if I go ahead and run this program, /sigma 0, and I type in a positive integer like 2, sigma, as the Greek symbol implies, it's just going to add up all the numbers from 0 on up to 2. So 0 plus 1 plus 2, so this should hopefully give me 3. That's all it's doing. And similarly, if I run this again and I give it the number 3, so that's 3 plus 2, so that's 5 plus 1, should give me 6. And then if I get really crazy and start typing in bigger numbers, it should give me bigger and bigger sums. So that's all. So what does sigma look like? Well, it's pretty straightforward. It's how we might have implemented this for the past couple of weeks. Int is going to be the return type. Sigma is the name, and it takes a variable m instead of n. I'll change that up top. Then this is just a sanity check, but we'll see why in a moment. Now I declare another variable sum, initialize it to 0. Then I have this for loop iterating, apparently for clarity, from I equals 1 on up to an equal to m, which is whatever the user typed in, and then I increment the sum like this, and then return the sum. So a couple of questions. One, I claim in my comment that this avoids risk of an infinite loop. Why would passing in a negative number induce potentially an infinite loop? Never reach m, but m is passed in. So let's consider a simple example. If m is passed in by the user as -1, irrespective of main. Main protects us from this too, so I'm just being really anal with sigma to also make sure that the input can't be negative. So if m is negative, something like -1, what's going to happen? Well, I is going to get initialized to 1, and then I is going to be less than or equal to m. Stand by. That was, let's nix this story. I didn't ask that question because the risk that I am alluding to is not going to happen because I is always going to be greater than. Okay, I retract that question. Okay, let's focus only on this part here. Why did I declare sum outside of the loop? Notice on line 49, I've declared I inside of the loop. But on line 48, I've declared sum outside. Yeah? Sure. So first and foremost, I certainly don't want to declare and then initialize sum to 0 inside of the loop on every iteration, because this would clearly defeat the purpose of summing up the numbers. I would keep changing the value back to 0. And also, what's another more arcane reason for that same design decision? Yeah? Exactly. I want to access it outside of the loop too. On what line? On 53. And based on our rule of thumb from a couple of lectures ago, variables are scoped really to the curly braces that encompass them. So if I don't declare sum inside of these outer curly braces, I can't use it in line 53. Put another way, if I declared some in here, or even within the for loop, I could not access it in 53. The variable would effectively be gone. So a couple of reasons there, but now let's go back and see what happens. So sigma gets called, it adds up 1 plus 2, or 1 plus 2 plus 3, and then returns the value, stores it in answer, and printf here is why I'm seeing it on the screen. So this is what we'll call an iterative approach, where iteration just means using a loop, a for loop, a while loop, a do while loop, just doing something again and again and again. But sigma is kind of a neat function in that I could implement it differently. What about this? Which, just to be kind of cool, let me really get rid of a lot of distraction, because this function is really quite simple. Let's whittle it down just to its 4 core lines and get rid of all the comments and curly braces. This is kind of a mind-blowing alternative implementation. All right, maybe not mind-blowing, but it's kind of sexier, right? To look at this so much more succinctly. With just 4 lines of code, I first have this sanity check. If m is less than or equal to 0, sigma makes no sense. It's only supposed to be, in this case, for positive numbers, so I'm just going to return 0 arbitrarily so that we at least have some so-called base case. But here's the beauty. The entirety of this idea, adding the numbers from 1 to n, or m in this case, can be done by kind of passing the buck. Well, what is the sum of 1 to m? Well, you know what? It's the same as the sum of m plus the sum of 1 to m minus 1. Well, you know what? What's sigma of m minus 1? Well, if you kind of follow this logically, it's the same as m minus 1 plus sigma of m minus 2. So you can kind of just, this is like, sort of, if you're just trying to annoy a friend and they ask you a question, you kind of respond with a question, you can kind of keep passing the buck. But what's key is that if you keep making the question smaller and smaller and smaller, you're not asking what's sigma of n, what's sigma of n, what's sigma of n. You're asking what's sigma of n, what's sigma of n minus 1, what's sigma of n minus 2. Eventually, your question is going to become what? What is sigma of 1 or 0? Some very small value, and as soon as you get that, your friend, you are not going to ask the same question again. You're just going to say, oh, it's 0. We're done playing this sort of stupid cyclical game. So recursion is the act in programming of a function calling itself. This program, when compiled and run, is going to behave exactly the same way, but what's key is that inside of a function called sigma, there is a line of code wherein we're calling ourselves, which would normally be bad. For instance, what if I first compiled this, so make sigma 1 /sigma 1, positive integer please, 50, 1275. So the function seems to be, based on one test, correct. But what if I get a little dangerous and delete the so-called base case and just say, well, I'm just making this more complicated than it is. Let's just compute the sigma by taking m and then adding in sigma of m minus 1. Well, what's going to happen here? Let's zoom out. Let's recompile the program. Save it, recompile the program, and then ready /sigma 1, zooming in, enter, positive integer please, 50. How many of you are willing to fess up to seeing that? Okay, so this can happen for a number of reasons, and frankly this week we're about to give you more of them, but in this case, try to reason backwards what might have happened here. Segmentation fault, we said last time, refers to a segment of memory. Something bad happened. But what was it mechanically that went awry here because of my removal of that so-called base case where I returned a hard-coded value? What do you think went wrong? Yeah? Good question. So the size of the number that I was summing up got so big that it exceeded the size of the memory space. Good idea, but not fundamentally going to cause a crash. That might cause integer overflow, where the bits just flip over and then we mistake a really big number for like a negative number. But that itself won't cause a crash, because at the end of the day, an int is still 32 bits. You're not going to accidentally steal a 33rd bit. But good thought, yeah. The method never stops running, and indeed, it calls itself again and again and again and again and again, and none of those functions ever finish because their sole line of code calls themselves again and again and again. And what's really happening here, and now we can kind of draw this pictorially. Let me go over to a picture for just a moment. This is a picture that will eventually flesh out in more detail of what's going on inside of your computer's memory. And it turns out that on the bottom of this picture is something called the stack. This is a chunk of memory, a chunk of RAM, that's just used anytime a function is called. Anytime you, a programmer, call a function, the operating system, like Mac OS, Windows, or Linux, grabs a bunch of bytes, maybe a few kilobytes, maybe a few megabytes of memory, hands them to you, and then lets you run your function using whatever variables you need. And if you then call another function, you get another slice of memory and another slice of memory. And indeed, if these green trays from Annenberg represent that memory, here's what happens the first time you call function sigma. It's like putting a tray like this on what's initially an empty stack. But then if that tray calls itself, so to speak, calling another instance of sigma, that's like asking the operating system, ooh, need a little more memory, give me that, and then it gets piled on top. But what's key here is that the first tray is still there because he invoked this second tray. Now, meanwhile, if sigma calls sigma, that's like asking for more memory, gets piled on over here. Sigma calls sigma, it's another tray that gets piled on here. And if you keep doing this, eventually, kind of map this visual to that chart, what's going to happen with the stack of trays? It is going to exceed the amount of memory your computer has. And as soon as this green tray exceeds the horizontal line above stack and above that word heap, which we'll come back to in the future, that is a bad thing. The heap is a different segment of memory, and if you let these trays pile and pile on, you're going to exceed your own segment of memory, and a program is indeed going to crash. Now, as an aside, this idea of recursion, therefore, can clearly lead to problems, but it's not necessarily a bad thing, because consider, after all, how, and maybe this takes some getting used to, how elegant or how simple that implementation of sigma was. And we're not going to use recursion all that much in CS50, but in CS51, and really any class where you manipulate data structures like trees or family trees that have some hierarchy, it's super, super useful. Now, as an aside, so that you as aspiring computer scientists are familiar with some of Google's inside jokes, if you go to Google and you look up what is the definition of, say, recursion, enter. As an aside, I pulled up a few. This was like 10 minutes of procrastination this morning. If you also Google askew, notice by tilting your head slightly. And then this one's perhaps the most atrocious of all, since someone spent like their day implementing this some years ago. Come on. Oh, wait. That's a bug. So running on one of the world's biggest websites are these stupid little Easter eggs. They probably consume a non-trivial number of lines of code just so that we can have little fun things like that. But at least now you get some of those inside jokes. Now let's take a look at some of the white lies we've been telling of late and start to peel back some layers technically so that you really understand what's been going on and you can understand some of the threats like shell shock that have now started to become on the forefront of everyone's attention, at least in the media. So here is a very simple function that returns nothing, void. Its name is swap. It takes in two variables, and it returns nothing. It takes in A and B. So a quick demonstration. We brought these up. We might as well take a little break here for just a moment and have a little something to drink. If someone wouldn't mind joining me up here for just a moment. How about you in the maroon shirt? Come on up. All right. Just the one today. Thank you, though. All right, and we have coming up who here? What's your name? Laura. Laura, come on up. So Laura, very simple challenge today. Nice to meet you. All right, so we have some milk over here, and we have some orange juice over here, and some cups that we borrowed from Annenberg today. And
Borrowed.
going to go ahead and give you half a glass of this. All right, and we'll give you half a glass of the milk. Oh, and just so that you can remember what this was like, I remembered to bring this up and on today. Okay, if you wouldn't mind, let's see, we can put them over your own glasses if you want. This will be the world from Laura's eyes. All right, so your goal, given 2 cups of liquid here, milk and orange juice, is swap the 2 contents so that the orange juice goes into the milk cup and the milk goes into the orange juice cup.
Do I get another cup?
I'm so glad you asked, though it would have been much better footage if you hadn't asked. But yes, we can offer you a 3rd cup that's empty, of course. All right, so swap the contents there. Very nice. Very good. Actually doing this remarkably carefully. And step 3. All right. Excellent. A big round of applause if we good for Laura. All right, we have a little parting gift for you, but let me take these. Thank you so much. So, a simple example, though, to demonstrate that if you do want to swap the contents of two containers, or let's call them variables, you need some temporary storage to stage one of the contents in so that you can actually do the swap. So indeed, this source code up here in C is representative of exactly that. If the orange juice was A and the milk was B, and we wanted to swap the two, you could try something creative by pouring one into the other, but that probably wouldn't end particularly well. And so we use a third cup, call it temp, TMP by convention, and put the contents of the OJ in that, then swap one cup, then put the OJ into the original cup, thereby achieving exactly as Laura did this swap. So let's do exactly that. Let me go ahead and open up an example that's actually called no swap, because this is not as simply done as you might think. So in this program, notice that I'm using standard.io.h, our old friend. I have the prototype for swap up there, which means its implementation is probably down below. And let's see what this main program is going to do for me. I first declare int x gets 1 and int y gets 2. So think of those as OJ and milk, respectively. And then I just have a printf saying x is this and y is this, just so I can visually see what's going on. Then I have printf claiming that I'm swapping the two. And then I print out a claim that they're swapped, and I print out x and y again. So down here in swap is exactly what Laura did, and exactly what we saw on the screen a moment ago. So let's go ahead and be sorely disappointed. Make no swap, and run no swap, zooming in on the output here. Enter. X is 1, y is 2, swapping swapped. X is still 1. X and y is still 2. So even though, frankly, this looks exactly like, albeit more technically, what Laura did, didn't seem to work. So why is that? Well, it turns out that when we write a program like this that has both main highlighted here and then another function like swap highlighted here, which it calls, the world looks a little something like these trays a moment ago. When main first gets called, that's like asking the operating system for a bit of memory for any local variables like x and y that main has, and they end up right there. But if main calls swap, and main passes to swap two arguments, A and B, orange juice and milk, it's not like handing the orange juice and the milk to Laura. What a computer does is it passes copies of the orange juice and copies of the milk to Laura, so that what's ultimately inside of this tray is the value 1 and 2, or OJ and milk, but copies thereof. So that at this point in the story, there is OJ and milk in each of these trays. There's a 1 and a 2 in each of these trays, and the swap function is indeed working. It's swapping them inside of the second topmost tray, but that swapping has no impact. And based on just some basic principle we've talked about before, and indeed just a few minutes ago, what might explain why changing x and A and B inside of swap has no effect on x and y, even though I passed x and y to the swap function? What's the key word here that might simplistically explain? I think you heard here? Return. Return, oh, not return. Let's go with one other. What's that?
Void?
Okay, so return, we could make return work in this story, but there's an even simpler explanation. Scope. I'll take scope. So scope, remember, where are x and y declared? They're declared inside of main right up here. A and B, meanwhile, are effectively declared inside of swap, not quite in the curly braces, but still in the general area of swap. And so indeed, A and B only exist within this tray from Annenberg, this second chunk of code. So we're indeed changing the copy, but that's not really all that helpful. So let's take a look at this a little lower level. I'm going to go back into this source directory, and I'm going to first zoom in here, and just to confirm that I'm in this bigger terminal window, the program's still behaving like that. Suppose now that this is not intentional. Clearly, I wanted swap to work, so it feels like a bug. Now, I could start adding a lot of printfs to my code, printing out x over here, y over here, a over here, b over here. But frankly, that's probably what you've been doing for a couple of weeks now in office hours and at home when working on PSETs, trying to find some bugs. But you'll see, if you haven't already, that problem set 3 introduces you to a command called gdb, where gdb GNU Debugger has itself a whole bunch of features that can actually let us understand situations like this, but more compellingly, solve problems and find bugs. So I'm going to do this. Instead of /noswap, I'm instead going to run gdb space /noswap. In other words, I'm going to run my program not in bash, our new friend today. I'm going to run my program noswap inside of this other program called gdb, which is a debugger, which is a program that's designed to help you humans find and remove bugs. So if I hit run here, there's an atrocious amount of text that you really never have to read. It's essentially a distraction from the prompt, which I'm going to hit Control-L to get up at the top there. This is the GDB prompt. If I want to run this program now, as this little cheat sheet on today's slide suggests, run is the first command that we meant to introduce, and I'm just going to type run up here inside of GDB, and indeed, it ran my program. Now, there's some additional output to the screen like this, but that's GDB just being anal and telling us what's going on. You don't really have to worry about these details right now. But what's really cool about GDB, if I do this again, Control-L clears the screen, let me go ahead and type break main. Thereby, when I hit enter, setting what's called a breakpoint at noswap.c line 16, which is where GDB figured out my program actually is, my function actually is. This we'll ignore for now, but that's the address in memory specifically of this function. So now when I type run, notice what's cool here. My program breaks at the line I told GDB to pause execution at. So I don't have to now change my code, add some printfs, recompile it, rerun it, add some printfs, save it, recompile it, run it. I can just walk through my program step by step by step at human speed, not at Intel Inside kind of speed. So now notice this line appears here, and if I go back to my program in gedit, notice that that is actually the very first line of code. There's line 16 in gedit. There's line 16 within GDB. And even though this black and white interface isn't nearly as user-friendly, this means that line 16 hasn't been executed yet, but it's about to be. So indeed, if I type print x, not printf, just print x, I get some bogus value there of 0 because x hasn't been initialized yet. So I'm going to type next, or if you want to be fancy, just n for next. But when I type next, enter, now notice it moves on to line 17. So logically, if I've executed line 16 and I now type print x, what should I see? 1. And now this is admittedly confusing. $2 is just a fancy way of, if you want to refer to that value later, you can say $2. It's like a back reference. But for now, just ignore it. What's interesting is what's on the right of the equal sign. And now if I type next again and print y, I should see 2. I can also now print x again. And frankly, if I'm getting a little confused as to where I am, I can type list for list and just see some context around the point I'm actually at. And now I can type next. And there is x is 1. Now I type next, oh, y is 2. And again, it is confusing because GDB's output is being commingled with my own output. But if you keep in mind, by glancing back and forth at your code or laying it out side by side perhaps, you'll see that really I'm just stepping through my program. But notice what happens next, literally. Here's line 22. Let me go over it, thereby moving on to 23. And if I print x now, still 1. And if I print y now, still 1. So this was not a useful exercise. So let's redo this. Let me go back up to the top and type run again. And it's saying the program is being debugged, has started already. Start it from the beginning. Yes, let's do this again. And this time, let's do next, 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 next. But now things get interesting. Now I want to step into swap. So I don't type next, I type step. And now notice it has jumped me to noswap.c line 33. If I go back to gedit, what's line 33? That's the first actual line of code inside of swap, which is nice because now I can kind of poke around and get curious as to what's going on truly in there. Let me print temp. Whoa, why does temp have some crazy, bogus garbage value? It hasn't been initialized. And indeed, when you run a program, you're given a whole bunch of memory by the operating system, but you haven't initialized any values. So whatever bits you're seeing here, even though it's this crazy big negative number, just means that those are the remnants from some previous uses of that RAM, even though I haven't myself needed it yet. So now I'm going to go ahead and type next. And if I now type print temp, what should I see? Whatever the value of a was, a is the first argument, just like x was the first thing being passed in. So a and x should be the same, so print temp should print me 1. So what you'll see in problem set 3 is a tutorial of sorts on GDB, but realize that this is the beginning of a look at a tool that will actually help you solve problems so much more effectively. What we're ultimately going to do on Wednesday is start to peel back a few layers and remove some training wheels. That thing called string that we've used for some time, we're going to slowly take that away from you and start talking about something more esoterically known as char star. But we're going to do this nice and gently at first, even though pointers, as they're called, can do some very bad things if abused, by looking at a little claymation from our friend Nick Parlanti from Stanford University, a professor in computer science, who put together this preview of what's to come this Wednesday.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers. Oh, goody!
That awaits you on Wednesday. We'll see you then.
And now, Deep Thoughts by Davin Farnham.
Why are we learning C? Why not A+?